We have received unmistakable scientific proof that the hot Big Bang was the start of the universe as we know it for more than 50 years. The universe was once smaller, hotter, denser, and more uniform, but it is now expanding, cooling, and filled with clumps such as planets, stars, and galaxies. Everything we see today was once condensed into a single point or singularity, which signifies the beginning of space and time if you extend all the way back to the earliest possible times. At least, we believed that to be the tale, but today we are far better informed than we were then. The Big Bang can no longer be considered to be the beginning of the known universe, and it is highly likely that the hot Big Bang corresponds to the creation of space and time. What then if the Big Bang wasn't the actual beginning? How quickly is the universe expanding as well? And will everything in the universe eventually perish? Let's find out. We find stars, galaxies, clouds of gas and dust, tenuous plasmas and radiation across the spectrum of wavelengths, from radio to infrared to visible light to gamma rays, in every direction we choose to look. Where did all of this start from? The universe is filled with matter and energy at all moments and in all places, regardless of our perspective. Nevertheless, it's only logical to suppose that everything originated somewhere. The cosmos must be asked the most important question of all, the one regarding our cosmological origins, and you must then pay attention to what it says. The cosmos as we currently observe it is expanding, rarefying, and cooling. The principles of physics allow us to extrapolate backward just as easily as ahead, despite the temptation to merely extrapolate into the future when objects are much larger, less dense, and cooler. The universe was denser, hotter, and smaller long ago. How far in the past can we extrapolate from this? In mathematics, it can be tempting to push the boundaries as far as they can go, all the way back to infinitely small dimensions, infinite densities, and infinite temperatures, or what is known as a singularity. The Big Bang was the name given to the concept of a single beginning for all of space, time, and the cosmos. Physically though, we have discovered that the world actually told a different tale when we looked closely enough. Here's how we know the cosmos didn't start with the Big Bang. The general theory of relativity proposed by Albert Einstein has been put to several scientific tests, resulting in some of the most severe limitations ever attained by mankind. Like most scientific tales, the Big Bang's origin has its roots in theoretical and experimental or observational fields. An innovative theory of gravity that intended to displace Newton's idea of universal gravitation, Einstein's general theory of relativity, was introduced in 1915. Even though Einstein's theory was much more involved and difficult, the initial precise answers were discovered quite quickly. Karl Schwarzschild's definition of a non-rotating black hole as a point-like mass was solved in 1916. The answer for an empty universe with a cosmological constant, which describes an exponentially expanding cosmos, was discovered by Willem de Sitter in 1917. Between 1916 and 1921, the spacetime for a charged, spherically symmetric mass was defined by the Reissner-Nordström solution, which was independently discovered by four physicists. Edward Kästner discovered a solution in 1921 that depicted a world devoid of matter and radiation that is anisotropic, different in all directions. The answer to the question of how to create an isotropic and homogeneous world in which all forms of energy, including matter and radiation, are present was found in 1922 by Alexander Friedmann. For two reasons. The last one was very fascinating. One is that it seemed to describe the biggest scales of our cosmos, where objects tend to seem alike generally everywhere and in all directions. Additionally, you would discover that the world it portrays cannot be static but must instead either expand or contract if the Friedmann equations, the governing equations for this solution, were solved. Many people, including Einstein, acknowledged this latter truth, but it wasn't given much weight until observable evidence started to back it up. Astronomer Vesto Slipher began observing some nebulae in the 1910s and discovered that they were moving very quickly, much faster than any other objects in our galaxy. These nebulae were thought by some to be galaxies outside the Milky Way. Furthermore, most of them were traveling away from us, with fainter, smaller nebulae appearing to move more quickly in general. Then, in the 1920s, Edwin Hubble started calculating the distances to the individual stars in these nebulae. They were not only far further away than anything else in the galaxy, but those at larger distances were also accelerating their distance from us. The universe was expanding, as Lemaitre, Robertson, Hubble, and others quickly realized. In 1927, Georges Lemaitre was the first to acknowledge this. He projected backward after discovering the expansion, assuming, as any capable mathematician might, that you could go as far back as you wanted to what he called the primeval atom. He understood that everything around us came from this early era when the universe was only a hot, dense, and expanding collection of matter and radiation. Later, this idea was developed by others who made the following additional predictions. We can notice that the universe is more developed now than it was then. As we look farther back in space, we are also looking farther back in time. Therefore, the objects we observe from that era ought to be more recent, less gravitationally clustered, smaller, made up of fewer heavy components, and have less developed structures. More importantly, there shouldn't be any more galaxies or stars. There should remain a remnant, now cool and sparse, a bath of cosmic radiation from this time, when the radiation was so hot that neutral atoms couldn't form steadily because the radiation would consistently kick any electrons off of the nuclei they were seeking to bond to. Big Bang nucleosynthesis suggests that there was an early pre-stellar phase where nuclear fusion would have taken place when it was so hot that even atomic nuclei would have been blown apart. As a result, we anticipate that before any stars formed, there was at least a small population of light elements and their isotopes dispersed throughout the cosmos. Together with the expanding universe, these four ideas formed the basis of the Big Bang. The expansion and evolution of the universe's large-scale structure, specific galaxies, and the star populations found inside those galaxies all support the predictions made by the Big Bang. The primary evidence that supported the Big Bang theory and disproved many of its most prevalent rivals was the discovery of a radiation bath that was only 3K above absolute zero, along with its blackbody spectrum and temperature irregularities at microkelvin levels of tens to hundreds. The ability to extrapolate back as far as your evidence will allow is a huge accomplishment for science. We are able to test our models, hypotheses, and understanding of the cosmos because the physics that occurred during the initial moments of the hot Big Bang left its mark on the universe. The universe's large-scale structure and the cosmic microwave background, which is the remnant radiation from the Big Bang, are both affected by the cosmic neutrino background, which is the universe's oldest discernible trace. Amazingly, this neutrino background was present for only a fraction of a second after the hot Big Bang. However, extrapolating beyond the bounds of your quantifiable evidence is a risky, though alluring, game to play. After all, if we can go back 13.8 billion years to the hot Big Bang, when the universe was only a fraction of a second old, what's the harm in going even further back to the singularity that was supposed to exist when the universe was 0 seconds old? Surprisingly, the response is that there is a great deal of harm. Beginning at a singularity, at arbitrarily high temperatures, arbitrarily high densities, and arbitrarily small volumes, will have effects on our universe that aren't always supported by evidence, which is why this is problematic. For instance, if the universe emerged from a singularity, it must have done so with precisely the proper amount of stuff, matter and energy combined, in it to balance the rate of expansion. The initially expanding universe would have already collapsed by now if there had been a teeny bit more matter. And if there had been just a little bit less, the cosmos would have grown far faster than it has now. However, the rate of the universe's initial expansion and the total amount of matter and energy present in it are all observed to be in perfect balance. Why? We have no explanation if the Big Bang originated from a singularity. All we can say is that the cosmos was founded this way, or, as physicists who don't know Lady Gaga put it, initial conditions. Similarly, we don't see any magnetic monopoles, which would be predicted to exist in a cosmos that experienced arbitrarily high temperatures. Even though the universe is observed to have identical temperatures everywhere with an accuracy of 99.99%, it would be predicted to have different temperatures in areas that are casually detached from one another, i.e., are facing opposing directions in space, at our observational limitations. We are always free to use the beginning conditions as the basis for any explanation and to conclude that something is the way it is because of how the universe came into being. But as scientists, we're always much more intrigued if we can identify a cause for the characteristics we notice. That and more is exactly what cosmic inflation provides for us. Yes, extend the hot Big Bang back to an incredibly early, incredibly hot, incredibly dense, incredibly uniform state. But stop yourself before you travel all the way back to the singularity, according to inflation. There must be a method to configure the cosmos to balance the rate of expansion and the total amount of matter and energy. The same holds true for a universe with uniform temperatures everywhere. A slightly distinct point is that in order to prevent high-energy relics from forming, you must find a mechanism to eliminate any that may already exist, while also preserving your universe from ever being too hot. The same approach discovered by De Sitter back in 1917 is used by inflation to propose a time previous to the hot Big Bang, when the universe was dominated by a big cosmological constant, or anything that behaves similarly. By capping the highest temperature that can be achieved when inflation finishes and the hot Big Bang ensues, this phase stretches the universe flat, gives it uniform qualities everywhere, eliminates any pre-existing high-energy remnants, and stops us from creating new ones. It also generates fresh predictions for the kinds of flaws the cosmos would have at its beginning by supposing quantum fluctuations were formed and spread throughout the universe during inflation. Since inflation was proposed in the 1980s, it has been put to the test against the alternative, a universe that emerged from a singularity in a number of different ways. Scientists discover the following when they stack the scorecard. There is nothing that the hot Big Bang can account for that inflation cannot also account for. Inflation reproduces all of its triumphs. The puzzles that we can effectively solve by stating starting conditions in the hot Big Bang are explained by inflation. 4 of the predictions that can distinguish between a hot Big Bang without inflation and inflation have been tested with enough accuracy. Inflation is 4 for 4 on those 4 fronts, whereas the hot Big Bang is 0 for 4. But if we go back to our concept of the beginning, things start to become extremely fascinating. An inflationary world cannot be extrapolated back to a singularity, but a universe with matter and/or radiation, what we get with the hot Big Bang, can. Space will only approach microscopic sizes, infinite temperatures, and infinite densities due to the exponential nature of its expansion. It will never reach them. This indicates that inflation absolutely cannot lead to a singularity on its own, as opposed to necessarily causing one. The instant we understood that an inflationary phase preceding the hot, dense, and matter and radiation-filled one we currently inhabit, the notion that the universe began to form from a singularity, and that's what the Big Bang was, had to be abandoned. 3 crucial facts regarding the universe's creation are revealed in this new image, which contradicts the conventional narrative that the majority of us were taught. First, the original theory of the hot Big Bang, according to which the universe erupted from a singularity that was infinitely hot, dense, and small, and has since been expanding and cooling while being full of matter and radiation, is untrue. Although there is a limit to how far back in time we can extrapolate the picture, it is still substantially accurate. Second, observations clearly documented cosmic inflation as the condition that existed before the hot Big Bang. Any prior elements of the universe were figuratively inflated away during the early universe's exponential growth phase before the hot Big Bang. When inflation came to an end, the cosmos overheated to a high temperature that was not arbitrary, giving rise to the hot, dense, and expanding universe that eventually developed into the one we live in today. Finally, and perhaps most significantly, we no longer have any understanding or confidence regarding how the cosmos originated or whether it did. By its very nature, inflation obliterates all knowledge that existed prior to the final few seconds when it terminated and gave rise to our fiery Big Bang. A phase that did originate from a singularity may have come before inflation. It could have come before some other non-singular phase, or it could have come before inflation for all eternity. We have no choice but to accept our ignorance until the time comes when we figure out how to extract more knowledge from the universe than it currently appears to be possible. Even though the Big Bang still occurred a very long time ago, it wasn't the beginning, as we always believed. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.